Hi, today I'm going to be opening a couple geodes. This one is a Keokuk geode that was mined in Missouri. It came from about 90 feet under the ground. The people that mined it have a lot of heavy equipment and they are able to go deeper. Usually in the Keokuk region, you do a lot of ground mining, surface mining, just finding what's already been revealed on the surface. This one is one of those. The color you'd most commonly see on the surface. This one, I'm not quite sure where it came from, but I do know it's a Keokuk. And then lastly, we've got this Truncus geode. This is one that I ordered from a guy on Etsy that had a whole bunch of them. As you can see, there's almost no rock on the outside. You can see the crystal formations on the outside. There's just a little bit of rock on the bottom. This one's kind of a wild card, especially because of its shape. And then this one's definitely a wild card because it's that 90 feet deep Keokuk geode, and I bought it from just a bucket, and the guy was like, yeah, I'm not going to give you any guarantees on those. We haven't graded them for hollowness. So that's what I'm going to be doing today. I'm going to show you some of the equipment I'm going to be working with, just to preface this. Not a scientist, don't know what I'm doing, but we're going to be looking at the specific gravity of a couple different types of rocks, and then also the specific gravity of these geodes and comparing them to see what their volume is and what their density is to see if they should be hollow inside. For this little specific gravity science experiment, I've got some paint cups that have volume markings on the side. I picked these up for a couple bucks. Honestly, I've gotten them for free before from paint shops, so you can find them anywhere. But you can also, since we're dealing with volume and we're going to be marking things and weighing things, you don't even need volume measurements. You just need a cup that you can mark on and see the water line through. I just thought that I needed these, so I went and got them. The other thing I'm going to be using is this super cheap little scale that I got from Walmart. This is what I use for baking bread and whatever. I'm usually very particular about food items and hobby items and never mixing the two, but I figured it's a scale, it's gonna be fine. I'm not putting food directly on it and I'm not putting rocks directly on it. Well, yeah, I am. But any sort of containers or measuring devices that you use, you want to keep those separate. I do a lot of dyeing, and if you're cleaning quartz with iron out, there's all sorts of crazy chemicals that you don't want to start mixing into your kitchen utensils, so I try to keep those as separate as possible. But I'm gonna go ahead and get set up over there and show you guys how I'm going to find the gravity of a couple different rock specimens that I have, so that we have kind of a baseline to compare the geodes to and then see how hollow they are. Let's go. So I've got a few rock samples here, pea gravel, some limestone from my driveway, and I have some quartz crystals. I'm going to measure out 100 grams of each of these samples so that we can measure their volume by seeing how much water they displace. I'm going to zero this out and measure 100 grams of my pea gravel. And 100 grams of my limestone. And 100 grams of quartz crystals that I mined last summer at the Fisher Mountain Claim on Mount Ida in Arkansas. Now I'm going to get another cup and fill it with 300 milliliters of water. I'm only using 350 because it's a line that I have on these cups, but since we're weighing the water, it doesn't really matter what amount we use, so long as you write it down so that you can compare the later measurements to it. I've got a clean cup and switched my scale to measure milliliters of water, which is basically still grams, as 1 milliliter of water weighs almost exactly 1 gram. I'm going to measure out 350 milliliters of water, and then we're going to pour it back because I can't measure. There we go, that's better. Now I'm going to add our pre-measured river rock, and we're going to mark the line that the water comes up to after we've added it. Now that we've got that mark, we can ignore this weight entirely because it's weighing the rocks. What we want to do is weigh the water that would take up the same amount of space. So now I'm going to pour everything out and fill it back up to that water line, which will give us the weight of the water that would take up the same amount of space that the rock was taking up. The difference between this new weight and the original 350 milliliters is the volume of the pea gravel. You really want to get down on eye level when you're pouring in this new water to see how it lines up with your line. It can be kinda hard to do if you're standing above it. Now our new weight is 396 milliliters, so those rocks displaced 46 milliliters of water. That's how much it rose when we put the rocks in. Dare I say, eureka? So now that we've done one, I'm just going to pause here so that I can explain what exactly we're using these numbers for. As you can see on the left, I've taken account of the weight, volume, and density. The volume is measured in cubic centimeters because a milliliter is essentially a cubic centimeter. And since we're not measuring water anymore, we're measuring the volume of the rocks, I'm translating everything into cubic centimeters. To find the density of the rocks, we're going to take its weight, 100 grams, and divide it by 46 cubic centimeters for a density of 2.17. We're going to do the same calculation for the rest of our rock specimens today, and then at the end we can compare our geodes to our baseline rocks and determine if they're hollow or not. If the geodes have a density that's less than our quartz or our limestone, then they're probably hollow. This river rock is a lot less dense than I expected, and I'm not sure if that's an error in my measuring or if river rock truly is that light. Now I'm going to repeat that process with 100 grams of quartz, gently placing them in the water because it does kind of splash and I don't want to lose any of that water. I chose quartz because Keokuk geodes have quartz inside, so I thought that would be a good comparison, the volume of a geode compared to a solid crystal. So again, I'm going to mark that line where the water's coming up to and pour all of this out. Now I'm going to get back on eye level and fill the cup up with water to that new line that we made when we put the quartz in. Okay, that looks pretty good. What we've got here is 348, which means that our quartz displaced 44 milliliters of water. If you take that initial 100 gram weight and divide it by the 34 milliliters that were displaced, you end up with a density of 2.94 for this quartz, which is higher than it should be, I'm pretty sure. And once again, we're just going to take these measurements with a ton of salt. So we've got our water again with 350 milliliters, and I'm going to add my 100 grams of limestone and mark this new line. I'm filling it back up to that new line, and we end up here with 385 milliliters of water, so 35 milliliters of water were displaced. This was surprisingly close to the quartz. I was expecting the limestone to be much less dense. Again, we're going to divide our 100 grams of limestone by its 35 milliliters of water displaced for a density of 2.84. Now, onto the main attraction, the geodes. I've got my cup with 350 milliliters of water, and I'm going to gently place this first Keokuk geode into the cup. This geode weighs 120 grams. I'm going to mark a line where the water is now and pull the geode out. Now I can pour water in up to that new line. My final volume of water is 409 milliliters, so this geode displaced a volume of 49 cubic centimeters. If we divide our initial weight of 120 grams by 49, we get a density of 2.03 grams per cubic centimeter. With the scale at 0, I'll add in the 350 milliliters of water. You'd think at some point I would pre-measure this. This guy is really heavy, so we'll see what this ends up being. After I put the geode in, I'll mark this new line here and take it out. Then we can fill the cup back up with water to that new line. On this geode, we have 391 milliliters total, so this geode displaced 41 milliliters of water. When we do our little math, we end up with a density of 2.44 grams per cubic centimeter. Our last rock is this funky Troncus geode. This one weighs in at 94 grams. I've got my 350 and I'll just pop them in there. Then I can mark that line and take him out. I don't know why this one got a gender. This one definitely looked like it displaced a lot of water. We've got 400 milliliters as our final volume, so the Troncus geode displaced 50 milliliters. To sum it all up, the river rock was weirdly not dense at all. I'm still curious if that's an error in my measuring. I might have to repeat this and see if I can get some more consistent results. I'm really excited about this Troncus geode with a density of not even 2. It should be incredibly hollow inside. The gray Keokuk definitely will be interesting because while it does seem to be less dense than solid rock, it's still definitely the closest to a 2.7 or 2.8 that you'd see with a regular solid rock. Alrighty, we've got the densities calculated on our 3 geodes. The Troncus definitely turned out to be the least dense, and you can feel it just by holding it, that it's super lightweight. And this guy ended up being our most dense, which I probably could have guessed, but still kind of cool to see the numbers and see when we open them up if we can relate those and if this is a good way to see how hollow your geodes are. I'm all bundled up because it's a little chilly out here. I'm gonna grab my trusty masonry hammer and head outside and crack these open. Let's go. First things first, I'm gonna put on my safety glasses, always important. And today I'm gonna be cracking these geodes with my trusty East Wing 20-ounce masonry hammer. It's pretty much my favorite, but as you'll see, not always reliable. Usually I get some pretty good straight and half cracks, but no one wanted to cooperate with me today. Farewell to the floofy boot walking away. This is the first Troncus geode. I'm gonna show it to you in the sun a little later. It's too far in the shadow here. Kind of shattered into 5 pieces. You can definitely see there's a lot of sparkle on this one. And really cool, almost river-like formations inside. Up next, I'm gonna crack the surface mined Keokuk geode. This one had a density of 2, so I'm really hoping for some good hollowness inside. Pretty easy crack at least, but it was incredibly powdery inside. I don't exactly know what all was in there, but it was a bit of a shock when it all came pluming out. You can see some of it blowing in the wind there when I hold it up. Now for the final Keokuk geode. This one had a density of 2.4, which is honestly pretty close to solid. And when I open it up after some intense desperation that I will not be showing you, you'll see that it was almost entirely grown in, but still had some gaps and open spaces. I wonder if I would have been able to see more if I had split it on a different axis, but there was no choice in this matter. Then I have to go look for the other half of that, and then I'll show you from the sunlight. Found it! As you can see, it is really grown in, but it's still really shiny and beautiful. Here's the other 2 little halves that split off. Quarters. Here's all the pieces of the Troncus geode in some slightly better light. You don't get that amazing sun reflecting, but a little easier to see all the different pieces that it broke into. Here's that first Keokuk geode that I cracked. I'm glad I got one solid half, but the formations on the smaller pieces were a little more detailed. The bigger piece is really just entirely powder inside for some reason. I've cracked some Geodes that have like pyrite powder or different things that have grown inside, but not just this weird white powder. And last but not least, we've got our almost entirely solid Keokuk geode. You can see where there's still a little bit of growing space, but it's not a whole lot. When you put it together, everything matches up really well. There are a few gaps where I think if it had been cut in a different way, maybe you could see more, but it was really solid.